Hello, my name is Faith Jean, and I'll be introducing Physics 2212 Lab 4, Circuits and Capacitors. The purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel, and examine the behavior of ohmic resistors and capacitors using the PHYS simulation, the circuit construction kit. The preliminary findings show that current in a 2-resistor circuit equals 0.02 amperes. Calculated values and experimental values for current and potential differences match. Greater resistance of a resistor in a circuit correlates to a longer time for the capacitor to charge and discharge, and the time constant, which is RC, is 5.984 seconds. Key concepts in this lab include the node rule, where at any node in an electrical circuit, the sum of the currents flowing in equals the sum of the currents flowing out, and the loop rule, where the sum of all electric potential differences around a loop is 0. Other key concepts in this lab include electrical resistance, which is the resistance in any component of a resistor, is equivalent to Ohm's law, assuming resistance is constant, and capacitance, which is the ability of a system to store an electric field. In a simple circuit, we constructed a circuit consisting of 2 batteries, 2 resistors, and 2 ammeters. The predicted current was 0.0204 amperes, the actual current was 0.02 amperes, and the reverse ammeter was negative 0.02 amperes. And this is demonstrated through the loop and node rule. In an open circuit, you create a similar circuit but having a voltmeter. The predicted values were the potential difference of 3 volts and the current was 0 ammeters, and the experimental values reflected that. Therefore, the experimental and predicted values agree. In measuring potential differences, you add all of the potential differences within the loop, and this finding supports the loop rule because all of the loops current add up to 0. For an ammeter in parallel, you reconstruct the circuit so an ammeter is parallel with the 100 ohm resistor, and the current measured by ammeters increases from 0.02 amperes to 0.06 amperes, as shown in the calculation below. Resistance can be calculated using Ohm's law, so R equals voltage over current. So the resistor of a 47 ohm resistor is 48, the resistance of a 100 ohm resistor is 102, the resistance of an ammeter is 0, and the resistance of a wire is 0. In this simulation, we measured the time to charge the capacitor and discharge the capacitor, so in both instances the current was 0, and we recorded the results with a 10 ohm and 20 ohm resistor. Preliminary results showed that the greater resistance in the resistor equaled a longer time for the current to equal 0 amperes. To determine the time constant for an RC circuit, you first need to construct the RV circuit using the 9-volt battery, 30 ohm resistor, and 2000 amp capacitor. You charge the capacitor and note the potential difference, then you remove the battery and pause the circuit in the PHYS simulation. For every second, record the potential difference as the capacitor discharges, and plot a natural log of voltage over voltage naught versus time. The slope of the plot equals -1 over the time constant, and then you would solve for the time constant. The slides demonstrate the graph of natural log of voltage over voltage naught versus time, and the RC constant was calculated to be 1 over 0.1671. Calculated resistance values are greater than the actual resistance of the resistors in the PHYS simulation, because ammeters are not very precise. Possible sources of error are the precision of the ammeter, rounding during calculations, and no consideration of resistance in ammeter and wires in real life. So what if we were doing this lab in real life and using an actual ammeter? What's different and how would this affect the circuit? A real ammeter has a non-zero resistance, and therefore this would decrease the circuit and decrease the readings. And what if we were doing this lab in real life and used a real battery with no resistor in the circuit? How quickly would our model predict the capacitor to reach charge, and would this happen in real life? The ideal model predicts the capacitor would reach full charge almost instantaneously. However, this does not occur in real life because wires have a non-zero resistance that would increase the time for the capacitor to reach full charge. Thank you for your time.